Hello YouTubers, Geo here with my second ever YouTube video, and a few days ago I did a video, one that I've been thinking about for a long time, about the theory of relativity and the skepticism I have about it. And years ago we didn't have YouTube, we had books, and I read books, and I came upon my skepticism based on just my logical thinking about what was written in those books, and just the belief or the realization that really there were some pretty significant logical disconnects in how the theory of relativity came about. And there was probably better ways that the physical world could be viewed that would be more useful, more constructive, and more able to allow us to explore further. And I think that the theory of relativity, because it's taken such a hold on us collectively, it's probably hindered the development of our understanding of our physical world, and that's too bad. Well, it is what it is. So anyway, since making that video, I've done a bit more thinking, and I've actually watched a few more YouTube videos about related topics. And so I just want to tell you about a few more things. I want to tell you about, I think I'm going to entitle this video, I haven't given it a title yet, but I think I'm going to call it Black Holes, Gravitational Waves, and Angry Men. I'll just say one thing. One thing I observe on YouTube a lot is people making claims. This is a scam. That's a scam. This guy is evil. That guy. They're lying to you. All these absolutes. And I think the world probably. I'm not sure that the world is usually very absolute. When I was a kid, I used to watch the Flintstones, and there'd be days, when Fred and Barney, I guess it was a Saturday, they didn't have to work, so Barney would go over to Fred's house and he'd watch the fights. And what the fights were in the Flintstones was these two cavemen, each with a big club, and they were clubbing each other over the head. And a lot of these YouTube videos I watch kind of remind me of those old Flintstones fights. So I'm not here to fight, but maybe I'm here to advance kind of the collective awareness and consciousness and evolution of humanity. That's what I hope I'm here for, but hey, who knows? Maybe I'm just talking. So anyway, but I digress. So back to the main topics. I came across some very interesting videos. I came across the usual, what would I call it, relativity apologia. People, the acolytes of relativity, and oh, it's the greatest discovery. It's changed us. It's very important for humanity, and here's why. Blah blah blah. There's a gazillion of those videos on YouTube, and largely just a bunch of baloney. Whether, I guess I just clubbed a bunch of people over the head. Well, anyway, I'm sure a lot of them actually believe what they're saying. But I did come across a few videos that I found refreshing, and I'll say one of them was called the World Science Festival, and it was the MC was a fellow named Brian Greene. I've heard of Brian Greene. He's a leading physicist. He wrote books, I think, Fabric of the Universe, those sorts of stuff. I might have even read some of his books, but I got to say, after watching that video, I had quite a bit of respect for Mr. Greene, and I also had quite a bit of respect for the people he had presenting, because they talked about relativity, and they talked about it in terms of questions they have about it, and how the actual observations they're making, because they're actually looking through telescopes of various types of telescopes, looking at phenomena in the cosmos, possibly black holes, neutron stars crashing together, all these different things, our galaxy, the way it's structured, the way the motion of different stars and so on in our galaxy. So they're doing some very interesting real world work, and they're not going to just give relativity a free pass. Um, and they basically said that in this video. And I'll put a link below to that video because I think it's worth watching. The other, I'm going to call this video Black Holes, um, Gravitational Waves, and Angry Men, because the other video is also a very good video by a fellow named Stephen Crothers, and I think he's from he's from Tasmania, a mathematician, a very direct speaker, um, very intense. I'm not sure that he's an angry man, but he's very intense and he's very critical of the mainstream use of the theory of relativity, misuse, I guess, what would you say, liberties taken with mathematics and logic, which I also discovered even my, I'm kind of a math midget, but I do, even not really having much background in math other than, basic engineering degree, still I encountered that. I discovered that too, that this relativity took on a life of its own, and people were willing or would take liberties with the mathematics, pretty significant liberties. And Brian Greene mentions, the fact that black holes involve dividing by zero. Well, dividing by zero, in the math world is really nonsensical. It's kind of not allowed. I guess if you divide by zero, the theory would say that the number you're going to get is infinity, whatever infinity is. So I suppose the density within a black hole, if it's derived by dividing by zero, you're going to have infinite density, which is going to result in infinite gravity, which is going to presumably result in the instantaneous destruction of the entire universe. So that's the sort of crazy stuff that more crazy stuff coming out of the theory of relativity. But to their credit, they not only do they recognize it, but they acknowledge it and they raise it up. So when they're talking about what they've seen, they're raising up these questions they have about the theory of relativity, as is Stephen Crothers, only he's doing it much more intensely and with no, I would say, probably with no funding or loss of funding attached to his conclusions. He's just saying what he thinks. Whereas these other guys, they've got, millions and millions of dollars being invested in their technology, paying their salaries, supporting so they have to be much more polite. Having said that, they're actually taking on what I think are the real issues. So give them credit for that. So, okay, so let's just talk a little bit about the actual what of all this stuff. So that's more the politics and personalities and all that. But the what of it. Okay, so let's start with black holes. So Einstein comes out with his theory of relativity in 1915. So of course that's when the war was on, First World War. Fellow Schwarzschild, or I forget, Schwartz something, comes up. He's actually in the trenches calculating trajectories for artillery in 1916, and he comes up with black holes. And there's like the escape, I guess the escape radius of a black hole, so kind of the radius beyond which, if you go beyond this line, you're going in. It's actually named after this fellow. And then this fellow was killed, or died, somehow, probably killed in the war shortly after he came up with the black holes. He wasn't the first guy to come up with black holes, though. There was a fellow in the 1700s, and this is what Brian Greene was saying, who, based on Newton's law of gravity, came up with the notion of a star that would, if it imploded in upon itself, it could become so dense that within anything within a certain radius of it would just get pulled into it. So that's an interesting point. I do black holes exist? Don't they exist? There's all these observations that have been made. I can't speak to whether they're real or whether they're misinterpreted, what they're seeing through the telescopes. I don't know. So, but I don't disbelieve it. I think that you could have, the idea of a neutron star makes a lot of sense to me, where a star has basically burned through all its fuel, and all that's left is basically this really hard neutron core. How dense would that be? Would it be dense enough to basically collapse in on itself? You know, that its gravitational field would be so. And then, I mean, black holes are, you know, basically more of the same. I mean, you've got something that just enormously dense material. Nothing can actually, nothing can move fast enough to get away from it beyond a certain radius. And presumably, as it goes through the universe, it collects more space junk. And who knows what's going on inside there? Who knows? I mean, we should be very open-minded about that and use our imaginations. I mean, is that stuff just going to a different dimension? Like this physical dimension that we believe is reality, is that just only one of many? And you know, when you have these black holes and stuff's going in there, you know, it's just coming out, popping out in a different, who knows? Or is it undergoing some sort of physical change of some sort? Is there annihilation of matter? I mean, there's all kinds of things that you could postulate, and I really think that's where we're at. Is, you know, even, you know, I'm not even sure they necessarily believe, you know, like they believe they can see. The thing about a black hole is it's black, so you can't see it. But I guess you can see evidence of it, especially if you see stuff swirling into it and so on. But I think they're still working on all that. I don't know that they've got proof positive that these black holes even exist. Anyhow, I guess my point is, again, with the theory of relativity, my major issue with it is that this whole idea of time dilation and so on, I don't think it was ever necessary. I think the evidence against the idea that the speed of light could vary depending on the speed of the source, I think that evidence was pretty shaky, and so really I'm thinking, well, black holes, yeah, why not? But again, why not start with Newton's law of gravity, and instead of monkeying around with time dilation, bending of 4D space and time and so on, just say, okay, we'll start with that. We'll start with Newton's gravity, but we understand that we got to keep our minds open to the possibility there's some really funky things that will go on when you get into really high densities and so on. And so we're going to use that as a starting point, and then we're going to study these boundary conditions. And we're going to study them in a number of different ways so we can try and figure out a better idea of what's going on. And we're not going to worry about relativity. We're just going to kind of push that aside for now. And I think that's really the gist of what Brian Greene and his panel were saying. And it's interesting because there's a woman there, this, what's her name? Andrea Ghez, and she's studying the middle of our galaxy, so the Milky Way galaxy, and she's postulated that there's a big, what, 3 million times the size of the sun, black hole in the middle of our galaxy, and that everything is kind of revolving, just there's everything is drawn to that. So there's revolutions, everything's revolving around that central black hole, and so she's used telescopes to map the trajectories of these different bodies. I guess that'd be stars, mainly, or solar systems or whatever, going around this central area, and then she says, yeah, we're going to, we'll apply general relativity, and we'll test it, and we'll see if it works. Like, so she's not saying, oh yeah, we're going to use the, relativity should describe. She's not saying that at all. She's saying we've got these, and she actually showed a 3D mapping of trajectories they've been following. She says, yeah, we're gonna do the math here, and we're gonna see if relativity is actually right. So great. To me, that's what we ought to be doing. And then there was a fellow, this Shep Dolman, and he was equally, I think, pragmatic and realistic. his approach was to look at radio waves. I think what was it? Radio waves coming from what he thought was what he believed to be black holes, and it was very interesting stuff. They collect radio waves in different parts of the world, and then they would use supercomputers to effectively turn the Earth into a giant parabolic telescope. Do the math and stack this data from various parts of the world together to get a much more, I guess, a clearer picture, a more powerful image. Very, very interesting stuff. And he had pictures of black holes, and he's got, you know, this Schwartz whatever radius, and then outside of that you've got kind of electromagnetic gas or whatever. So you've got effects that are theorized effects of substances that kind of just escape the black hole and so on. And again, he said the same thing about relativity. He said, yeah, you know, we're not going to take it at face value. It's got to be. I mean, it's part of science. We got to test it. Let's see if it works. So I think that's very positive, and hopefully, collectively, you know, people are, you know, saying, relativity. I mean, it's a theory. It's got to be proven, and it should be challenged, because you know, we're looking for the truth. We're actually looking. We're actually trying to understand what's going on. This is not all political. Okay, so that's black holes. So from my perspective, I think, yeah, makes sense. Black holes. I mean, if you have something that's dense enough, collapses in on itself, and the gravity, the forces of gravity become so strong, light can't even get out because gravity is so strong it's pulling it in. So I think, yeah, that could definitely happen. And then there's that leads to a lot of questions like, what's going on inside them when it's that kind of environment? What actually happens to matter? You know, what is happening in there? Okay, so on to gravitational waves. So gravitational waves are fascinating to me. A few years ago, I was watching the news, and then these guys came up and, hey, hooray, we've proven Einstein's theory that gravitational waves exist. So these guys were doing their victory lap because they'd proven it. And I remember looking at that and thinking, okay, you guys go ahead. I mean, victory laps are done in very many different contexts. It's kind of human nature to, you know, cheer for your team when you score a goal or whatever. So that's what these guys were doing. And of course, in my cynical mind, I'm thinking, well, you know, I'm sure they got tons of funding behind this, so they better show something. They better show success. I mean, you know, I don't know how much more funding they would have gotten if they'd, or even if they'd have been on the news, if they'd have come up with the conclusion, you know, we spent $1 billion, but it looks like maybe these gravitational waves, they actually don't exist. I'd probably the checks would stop being written probably the next day. So anyway, I think when you see these announcements, you have to kind of take them with a grain of salt. Having said that, and then this Stephen Carruthers, I mean, he's you know, in his very intense way, he actually waded through a lot of the math and so on, and really criticized the work that was done with gravitational waves. Now, again, I'm not here to do a Flintstones fight day. I don't need to beat anybody over the head with a club. I'm just trying to find the truth. Not this. So, what's the deal with these gravitational waves? Well, you know, I don't know if you may or may not have watched my last video, but you've got this notion of the bending of space-time in relativity, which again I'm really skeptical about. But the analogy that is most commonly given is the idea of a stretched rubber sheet with a bowling ball in the middle. So the bowling ball is a big mass, and if you put a marble on the outside edge of the sheet, it'll roll towards the bowling ball because the giant mass has bent space-time. And then, but then they say, okay, well, what if you just put a shock in there? Like, what if you, instead of dropping a big mass in there, you just kind of hit that thing quickly with something? Well, wouldn't that send a shudder through the rubber sheet? And so you would have a shudder or a wave moving through space-time. And that's it. I mean, that's basically the theory behind gravitational waves. And so they've developed some fascinating technology to try and prove or disprove gravitational waves. These interferometers, where they've got these 4-kilometer long pipes at right angles to each other in a couple of locations in the United States, and now they have one in Italy as well. They may have more now. This was a couple of years ago. So these pipes are evacuated, so there's no gas in them, so they're vacuums. They've got, it's a megawatt of power they put through into a very powerful laser light that they put through these pipes, these evacuated pipes. Now a megawatt, I mean, that's the size of a regular size, average size power plant. A megawatt, that's a lot of power. So they're not fooling around with this stuff. And then they've got these very precise mirrors, and they've got a mirror at a 45-degree angle. It's kind of a half silvered mirror, kind of that sort of, that splits the beam of this laser light, and then the laser light goes down, and then there's another mirror at the end of each of these 4-kilometer long legs that reflects the beam of light back, and then they can match up whether that beam, the two beams that were split off the original single beam of light, whether they're out of phase at all in their wavelength. And so they should be in phase, I guess, with all things being equal. But if you have a non-symmetric gravitational field working on these things that are at a right angle, then that will theoretically put the light waves out of phase, because it might stretch, this gravitational field might compress or stretch one of the legs relative to the other one. So that's the theory. And I just one thing about that is this is the far reaches of, I think, what our technology can actually achieve for measuring. So I mean, there's a lot of very precise things that have to, like when I'm curling, I had a fellow on my team. He says, George, you could just do this shot and that will solve everything. And I told him, I said, I suppose that's right. I said, but a lot of things have to go right for me to actually make that shot. And I think this interferometer stuff to try and measure gravity waves is a similar sort of thing. I mean, a lot of things have to go right, and maybe these guys, maybe they are going right, and maybe they are actually measuring stuff, and it could be gravitational waves. And I think that's quite possible, because if you think about gravity, if you think about even just the basic concept from Newtonian physics of gravity, I mean, you've got, and I did this with my last first equation for gravity. There it is right there. So you got gravity. Force equals G, which is a constant, gravitational constant. Mass 1 times mass 2 over r squared. So basically it's just an attractive force between two masses. And so if you have a very massive black hole or whatever in the universe, well, then it's going to, that's huge mass. And then you with the light wave or whatever, the tube that the light's going through, that's a much smaller mass, and so that's M2, and M1 is the black hole, and so on. So yeah, like, to me, I think we're all connected by gravity. The whole universe is connected, but the impact that something hugely massive a long ways away from us will have on us is, gravity-wise, is minuscule. So if you have, and in this case, the first, when they were doing their victory lap for the gravity waves, They said that they could match this up with two black holes that were spinning around each other, and then ultimately they were in a death spiral or a death spin or whatever. So they were spinning around each other, but they were attracting each other. They were two very dense objects attracting each other, spinning around, and you could see the oscillations in the readout for the interferometer here on Earth. And then kaboom, the two things smashed into each other. The two black holes smashed into each other, and that created a big blip, gravity blip. And I think, okay, well, yeah, I mean, there's a lot of reasons why that, it's just using Newton's gravity, why that's possible. Like, if you think about it, these two black holes or neutron stars or whatever spinning around each other, they will have a gravitational field that will be time variant, based on them spinning, right? It'll, of course, like they'll be moving around in space over time, and it'll affect the gravitational field around them, and it'll cause motion, I would think, of things around them, because as things are attracted to them, they're going to move towards them, and then so they're going to have an impact, and then kaboom, they come. Now, what happens when they, like, I think they said they lost a bunch of these two black holes lost a bunch of density, or lost a bunch of mass when they smashed into each other. Well, again, if you go back to the basic equation, you've got mass 1 attracting mass 2 divided by r squared. That's the basic relationship. Well, if all of a sudden this mass 1 becomes much, much less massive, well, then the force of its gravity, I guess, so the Newtonian theory goes, would immediately be much less, right? So if you're even, if you're near that massive object, all of a sudden the pull you're feeling from it would be much less, just by basic Newtonian gravity. So, I think, yeah, I would not doubt that there's all kinds of stuff. And then the other woman was talking about it. It's Andrea. No, there's this Vicky Calogera, I think was her name. She was talking about neutron stars, I guess, which are smaller, but she says, they're smaller, but the great thing about neutron stars is that they also emit radio waves when they collide. And so we can match up radio waves with gravitational waves. And I think, I don't doubt that. And so I guess to me, a big question is, when those things smash into each other, do they shed mass? What's going on with the actual matter there? To me, that's the big question. Forget relativity. But the other thought I have is, we in the 1800s, when Maxwell's equations came out, from those equations came out the conclusion that light was only a minuscule sliver of the much larger electromagnetic spectrum. And now it looks to me, maybe I'm wrong, but it looks to me like we have a situation where gravity waves are moving at the same speed as radio waves. I mean, otherwise, how could you match up neutron stars colliding and gravity waves? And if that's the case, couldn't you draw the further conclusion or postulate that gravity is another form of, in the genre of electromagnetic waves, somehow? So to me, I think that's an interesting thought, because the nature of gravity, and actually, you talk about, but they are talking about a quantum theory of gravity where they attribute gravity to particles, which, as you know, well, as you may or may not know, electricity, electromagnetism. I mean, you've got electrons now, positrons, and that sort of thing. So they're postulating things like gravitrons and anti-gravity and all that stuff. So to me, that's much more interesting. So anyway, there you go. black holes, um, um, black holes, gravity waves, angry men. And maybe Stephen Crothers isn't angry. Maybe he's just intense. And but one thing Stephen Crothers said, and I thought this was a good. I mean, it was sarcastic, but I guess he had challenged somebody about relativity, and the guy says, "Well, I know all these things that I see are real because I've seen them. Like I know quasars are real or whatever because I've seen them." And Crothers says, "Well, that's like a fishmonger um, saying, or no, he says, I know." The guy said, "I know relativity is real because I've seen quasars or something like that." So we postulated using relativity that these things existed, and then I've seen them. And Crothers says that's like a fishmonger saying that I know that relativity is true because I've seen fish. You know, the gist of it is these things that we're studying, these things that are various telescopes and such are seeing, you know, the cosmos. You know, I'm not saying that's not real. I think there's a whole bunch of very interesting observations and such that are being made and studies and so on. And a lot of them have been described using relativity. And that all I'm saying is I'm not sure that the relativity is the right way to describe them and maybe correct, really. Might work in some cases just because it's derived from things that are more correct, like Newton's gravity. Yeah, that's all I'm saying. So a lot of this stuff, hey, we should still think about it. We should study it definitely. Yeah, and maybe again, while we're doing that, consider all sorts of wide open possibilities, including other dimensions, including the impact of consciousness on reality, all kinds of things. Let's not limit ourselves, and also let's not limit ourselves by saying we have to, you know, mindlessly adhere to relativity, which maybe it's time. In fact, pretty clearly to me, it's time we move beyond it. We recognize that it's part of our history, and then we move beyond it. So that's my thoughts on black holes, gravity waves. Geo out.